All right, here we are once again, guys. Just math, y'all. Cal 1. We are doing limits at infinity. So this is section 2.5. Section 2.5. All right, let's find 2.5. That's 2.4. There we go with 2.5. Limits at infinity and horizontal asymptotes. If you remember horizontal asymptotes from your pre-calculus class, this should be familiar. We are going to do it slightly different. But the rules are kind of the same when it all boils down to it. But this time, we're taking the limit as x goes to infinity. We're not looking at x going to a number. We're looking at x going to infinity. Okay, and this, if we have a number that x goes to, that the function goes to as x goes to infinity, then we have what we call horizontal asymptote. All right, so let's look at some examples of this. And we're going to look at a second situation very similar to the one we looked at before, because this is rational functions again. And so rational functions again, these are the ones we have to deal with for the most part. So, what happens as x approaches infinity or x approaches negative infinity? Okay, so that's what we're looking at this time. So for a rational function, again, we're looking at 1 over x or 1 over something. And that's the most simple um, application there. And basically, as that denominator, as that number gets really, really big, what's going to happen to the value of the actual fraction? Well, this one's a little more intuitive because we know that that denominator means how many pieces that we cut it into in a fraction. And so as that number gets really, really big, the actual value of the fraction gets very, 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 very small, really small. And so just kind of to give you an example of this, say we had 1 over 10. Well, that's 0.1. 1 over 1,000. Well, that's 0.001. Okay. And then, as this number gets really, really big, like say 1 million, that's really, really big. But the actual value of this fraction is really, really small. So as the denominator gets really, really big, or as the denominator goes to infinity, the absolute, the actual value, not the absolute value, that's not, we're not going there. No, 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 no. The value of the fraction, as the denominator gets really, really big, the whole fraction is actually getting very, very, very small, smaller and smaller and smaller and smaller, closer to zero. And so the limit as x goes to infinity of 1 over x is always going to be 0. Whether it be 1 over negative to negative infinity is also going to be 0. So this is one of the big ideas of limits to infinity. There are a couple of other limits to infinity that we need to look at as well. So now, what if we did the limit as x goes to infinity of a power? Well, this is intuitive. It's not nearly as complicated as it may look. For example, if I did the limit as x goes to positive infinity of x to the fourth, well, as x gets bigger and bigger and bigger and bigger, this thing's just going to get bigger and bigger and bigger and bigger. Okay, this is going to go to infinity because we're just getting bigger and bigger and bigger and bigger. Okay, and so that's for an even power. For an odd power, we have the negative to have to deal with, and so as x goes to infinity, let's say x to the fifth, well, this is just positive infinity. But when we have a negative infinity, limit as x goes to negative infinity of x to the fifth, well, this is going to be negative infinity. Now let me explain that. It's very intuitive if you just plug it in. I mean, if you think about it, x goes to negative infinity of negative infinity to the fifth. Well, we know anything that's negative raised to an odd power is going to give me a negative. So a little intuition there. And then the last one is kind of like one of the limit laws that I haven't really gone over yet. This is intuitive. Is this number in front? If we have a number front, we can just multiply it in the front and it might change things. So like if I had a limit as x goes to infinity of negative 3x to the fourth, well, that would be negative 3 times, take it, the limit of x goes to infinity of x to the fourth. And then this would be that. And so now we're back to negative infinity for that one. So a little bit of difference going on there. Write down these rules. Go back to the video before I wrote red everywhere and just get the rules down, and it's going to be fine. So let's do a couple of quick examples. All right. So this one, this is negative 17x over, negative 17 over x to the 6th. Remember, negative exponents are actually denominators. And our rule says that this is going to go, as this number gets bigger and bigger, the whole thing's getting closer and closer to 0. There's not a positive or negative 0, so this one, the answer is just 0. This one, again, we can use those limit laws to separate this or not. It doesn't really matter. The limit as x goes to infinity of a constant is just a constant. This is going to go to 0. So 7 plus 0 is 7. So this one's 7. Let me put the infinity here. Sometimes you need to see infinity to the 6th power. That's 0. Infinity there, and that's 0. All right, so now the third one, we have, let's plug in the infinity. Let's try it that way. Let's see if that makes more sense. That's infinity times negative 3, so that's negative infinity. Does adding 5 change anything to negative infinity? No, it's still negative infinity. Let's plug negative infinity into this one. I have trouble making infinities sometimes. There we go. That is negative infinity. Times negative 4 is positive infinity. If I subtract 7 from positive, does that change? No, that doesn't change. So this one is positive infinity. Okay. All right. I'm going to make this a shorter video. I'm going to go and make video number 2, and we'll see how it goes. So come back and join us for video number 2 for some more examples.